Okay, we look at this third case. We have a straight rod of mass M and length L is rotated about one of its ends with a constant angular velocity. You have to find the tension at the point distance r from the point of rotation. I call that point O. This is the point of rotation. It's rotated. This point O is through this the axis of rotation is along this point O. All right. Now this is a strip. It could be a metal strip, a wooden strip. The total length is L, and we want to find the what is that again? We have to calculate the tension at this point. This point is point P, distance r from the axis of rotation up from point O. How do we go about that? Now to do this, we need to look at this other diagram, and you need to understand a particular concept here because we're bringing out the ideas of differential mass and differential distance here. Now the tension in this particular, in this part of the strip or at point P is, contributed by only the outer mass. So all the masses from here to point O will not be part of the tension, at point P, distance r. So the tension is contributed by the masses outside point P, from point P to this other end of the string, which I'll show you later. So try to derive an expression for the tension at point P. Okay, so I'm taking a differential element because just like you have this, let me use an example because you need to understand this concept of differential mass. Suppose the total length of the strip is, let's say 10 centimeters, is total length, and the total mass of the entire strip is 100 grams. Now, what we say mass per unit length? If we divide the mass by the length, divide 100 by 10 is 10 grams per cm. Okay, so that's the mass per unit length of the strip because you have to apply that idea here too. So that if I have to divide this entire strip into, let's say, 5 equal parts, one, this is 2, 3, 4, and 5. 5 equal parts, a uniform strip. It means that the distance or the length of each division, each part is 2 cm since the total length is 10 cm. Okay, so if I want to find the mass per unit length, of course, this is the mass per unit length rather. If I want to find the mass of one of the parts, okay, so I'll take that as my dm. My dm is now the mass per unit length, which is 10, and this mass per unit length is my m over l times this my 2 cm 2. That will give me 20 grams. So which means for me to know the differential mass, I need to know the mass per unit length, and I need to know the differential length. So this my 2 cm is like my dx, given that the total length here, for instance, is x. So this is my dx since it's divided into 5 parts. So each part is dx. So to find the differential mass, I have to find the mass per unit length. I have to know that m over l multiplied by dx, the differential distance. So that has to find the differential mass. So we need this idea to help us make progress in this derivation because we want to derive an expression for the tension in the string. So I take a differential mass. Now the tension at, of course, I told you earlier, at point P is contributed by the mass of the strip that is outside point P, that is to the right hand side of point P. So let's say the tension for this small mass, that is cut out is T. The tension is T. It means that the tension from here for this small mass, the tension is the T, that is differential tension, because since it's a differential mass, differential distance, then the tension to the differential tension. So the tension from this end to this end is going to be T plus differential tension dt. All right. So if I want to find the tension for this small element of the strip, is going to be T minus dt or T plus dt minus T. That will still give me the dt, which is the tension for this small mass, differential tension. And it is given by, of course, I got this by saying T plus dt minus T. So that will still give me the T, which provides the centripetal force. So I can equate it to my centripetal force, which is m omega squared multiplied by L. But since I'm dealing with this small mass, so I can use my dm for my m. I can use my omega squared times for my x. I can use times x because I'm looking at from the distance from here to this end. Because the tension is measured, our main point, the differential mass is taken from here to this axis of rotation, which is point O. So that distance is x. But I'll come here, what's my differential mass? My differential mass is m over L, that is total mass over total length multiplied by the differential distance. So my dt here now will be equal to, here I'll put my m over L, maybe in a bracket, parenthesis, multiplied by dx, or omega squared x multiplied by dx. So this my dx is my dx here. So what do I do? The next thing is for me to integrate. Yes, to find the tension acting from point P. I mean the tension at P. So I have to integrate. So integrating, I'm going to take my limit of integration from R, because we are looking at, remember I said that the tension at P is contributed by this outer mass of the strip. So I'm going to say this total length, which is L, minus this length from here to here, gives me from here to here. That is the total length minus this distance will give me what I need from here to. So I'm integrating from this lower limit to the upper limit. Dt is equal to integral. I have my m over L omega squared x dx. I'll still integrate between, this time around I'm integrating between, also between L over R. All right, I have some constant there of integration, which we are going to factor out of this bracket. So integrating this, I have TR, okay, that between this and this is equal to m over L is a constant, omega squared is a constant, integral from R to L x dx. Okay, so I need to integrate this now. Okay, let me move to a different page. So TR gives me m over L omega squared, integrating x dx. For those of you that have gone through this integration, it's very important here to know what to do here. So you have to take some lessons on integration if you have not done that already, over 2. Because to integrate x, it is given as x squared over 2. The general rule for integration is if you're integrating an algebraic expression like x dx, this is xn. So it is given as xn plus 1 over n plus 1 plus c. But if there are limits of integration, we don't need the arbitrary constant. So this is the rule, xn plus 1 over n plus 1, where n is integer here in this case. So it is 1 here. For my x is 1, so I have to 1 plus 1 over 1 plus 1, that is x squared over 2. All right, so that's how to quickly do the integration there. So we have TR equals m over L omega squared. Then I'll substitute my interval. This 2 is a constant. I can bring that out. I'll now replace my interval of integration. Put when when x is L, have x squared, L squared minus R squared. Okay, so my TR will be equal to m omega squared over 2L into L squared minus R squared. So this is the tension at point P from what we did here before, from this diagram, okay? Now you can come to see that at the end of the strip here, at the end of the strip, let's see the tension there. At that point now, my distance R is equal to L at the end of the rod. Okay, so if I put that here now, making my substitution, I have m omega squared over 2L. That will give me L squared minus L squared. Okay, so substitute, that is replacing R with L. So the tension there is equal to 0. So at the end, there's no tension. The tension will be contributed because there's no other mass beyond this end of the strip. So that then the tension is maximum at point O. Okay, so that is when R is equal to 0. That is at point O. That is the axis of rotation at point O. So I have TR is equal to m omega squared over 2L into I have the L squared minus 0 because R is equal to 0. So the tension there gives me M omega squared L squared over 2L. I can divide this by this. That gives me M omega squared L over 2. So that gives the tension at the end, which is maximum at the point of rotation, that is through the axis of rotation. So this is how to kind of determine the tension, at a particular point on the strip. Okay, I guess you understand this. So take your time and go through it so that I can really follow up on it. So the next video will take more on this.